Welcome back to another explainer. Today, we're unpacking the immense, honestly mind-blowing technical challenges of rendering complex 3D worlds in real time. We're going to take an incredible journey together, starting with the microscopic details of a single virtual asset and zooming all the way out to the literal cosmos. Okay, let's dive right in by considering the sheer impossibility of what our computers pull off every single day. Just imagine having to calculate the light, the texture, and the geometry for millions of pixels, and doing all of that 60 times a second without completely melting your hardware. How on earth do we build systems smart enough to do this? Well, to understand how developers pull off this magic trick, here's our roadmap for today. 1. The real-time rendering challenge. 2. Mastering microdetails with Spire. 3. Optimization and auto-tuning. 4. Navigating the virtual cosmos. And finally, number 5, curing VR sickness. Let's kick things off with Section 1, the real-time rendering challenge. So the crucial thing to understand here is that rendering any modern virtual world requires constant, calculated compromise. You're always playing this massive balancing game between wanting photorealistic visuals and hitting the harsh physical limits of your computer's processing power. To really grasp the big stuff, we actually got to start small. Shaders are your fundamental building blocks for real-time graphics. Think of them as the tiny little programs that figure out the exact color of every single blade of virtual graphs. Now, managing a handful of these? Easy. Managing tens of thousands of them at once? That is an absolute logistical nightmare. Moving on to Section 2, Mastering Microdetails with Spire. Enter the Spire compiler framework. You can kind of think of Spire as a movie director. It strategically hands out computations to different stages, or what its creators call worlds, across the whole rendering pipeline. Instead of forcing your GPU to frantically calculate everything right at the exact millisecond the frame is drawn, Spire distributes the workload. Maybe it bakes some calculations into an offline texture map and saves only the absolutely critical stuff for real-time fragment shading. It's all about balancing that high visual quality with raw performance by completely separating a shader's core algorithm from its execution schedule, which really just means when and where the math happens. Spire lets a single terrain shader spawn multiple optimization variants. For example, if you're strapped for performance, you can swap out a really heavy real-time lighting calculation for a simplified model, or just pre-bake the texture offline. It's the exact same base shader, it's just executing differently based on what the hardware can actually handle at that moment. Which brings us to Section 3, Optimization and Auto-tuning. I absolutely love this analogy. Optimizing graphics is essentially like baking a cake. You have to decide, are you going to painstakingly decorate every single slice right before serving it? That gets you high quality, but it takes forever. Or do you bake those decorations directly into the batter? That gives you high performance. Spire seamlessly manages this exact trade-off between super expensive per fragment shading and highly efficient pre-baked textures. When you use Spire's automated systems to dictate the level of detail across a massive scene, we're talking 10,000 distinct objects. Researchers found it slashed the frame rendering time from 33 milliseconds down to just 17. It literally cuts the time in half. And the best part, it maintains an incredibly convincing visual illusion. The computer gets massive relief and the player doesn't even notice a difference. What's even wilder is Spire's ability to grade its own homework in a matter of seconds. It'll automatically pick a high-end microfacet lighting model for a beefy graphics card like a GTX 980 Ti, giving you the best visuals possible. But the second it detects a weaker GPU like a GT 720, it cleverly auto-tunes itself. It downgrades to a baked texture variant so your game keeps running smoothly instead of just crashing your entire system. Talk about smart resource management. Okay, so that covers the microscopic stuff, your grass, your couches, but it brings up a really huge question. What happens when you need to render something exponentially bigger? I mean, what if your virtual world isn't just a terrain map, but the literal to-scale solar system? Let's zoom out for Section 4, Navigating the Virtual Cosmos. To really grasp the sheer scale we're talking about now, imagine exploring Martian terrain, specifically Gale Crater, using actual data mapped by the Mars Reconnaissance Orbiter. Now imagine that projected immersively into a room-sized cave system running on 28 different projectors.
We're looking at a framework designed specifically to handle unimaginably massive space mission datasets in real time.
But there is a massive mathematical roadblock here. At this cosmic scale, standard GPU math completely falls apart. See, your computer uses standard 32-bit floating point numbers, great for normal video games, but you absolutely cannot use those standard numbers to track something as gigantic as Jupiter while simultaneously tracking something as tiny as a Mars rover's tire tread. You instantly lose precision, and the graphics will just begin to tear and artifact all over the place. To fix this, a framework called Cosmos Scout VR relies on SPICE. SPICE is this highly precise, double-precision coordinate system that is literally used by NASA. By linking their scene graph with SPICE, Cosmos Scout dynamically scales the entire universe around the user. So, mathematically speaking, the closest celestial body is always placed within arm's reach. That ensures you keep your spatial context and absolute pinpoint accuracy, whether you're staring down a galaxy or a single pebble.
And that brings us to our final stop, Section 5, Curing the VR Sickness.
You see, navigating a true-to-scale solar system creates a very biological problem. Seamlessly flying between planets at millions of miles an hour in VR, yeah, that introduces the challenge of keeping the user from throwing up. Because there's no real concept of up or down in space, Cosmos Scout fights cybersickness with two really clever tricks. First, to stop you from losing your balance, they project an artificial stability grid on the floor. Second, to fix that dizzying illusion of self-motion, which is called vection, they use a vignette to artificially narrow your field of view during high-speed travel. It basically tricks your inner ear into staying perfectly calm. There's also the headache of mapping data onto these massive planets. To keep planetary terrains rendering smoothly without glitching out at the poles, like if you were trying to render the complex ice caps on Mars, Cosmos Scout uses a specialized HeelPix map projection. Traditional digital globes pinch all their data at the top and bottom, which causes massive lag. But HeelPix provides a singularity-free subdivision, which is just a fancy way of saying it maintains a totally uniform data density across the entire planet. So whether we're talking about the Spire compiler intelligently caching lighting to save a few milliseconds, or Cosmos Scout VR dynamically scaling the entire Earth to fit seamlessly inside a giant planetarium dome, both of these systems rely on incredibly smart resource management. They literally bend the rules of computation to make the impossible feel completely real and totally immersive. I'm going to leave you with this final thought to take away from our explainer today. As our rendering technology continues to effortlessly bridge this massive gap between a single millimeter and an entire light year, what completely new, impossible universes are we going to create next? Thanks so much for learning with me today. I'll see you in the next one.